Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the first module of this course, that is the introduction module. And the idea behind this module is to give you a basic introduction to operating systems. So within the first module we are on the second topic, that is introduction to operating system. And in this topic, we are trying to understand what is an operating system and what does it do. So as we know, the operating system is a special piece of software that manages the computer hardware. So starting from the previous video, what we have been doing is that we are focusing on each of the individual hardware components and seeing how the operating system manages that particular piece of computer hardware. So we have already talked about the CPU in the previous video. Now let us focus on the memory and see how the operating system manages the memory. So let's get started. So before we talk about how the operating system manages the memory, let us quickly recall why do we have the memory in the computer system. So basically memory is the place where all the data and the instructions are kept while the CPU is processing that information. So we as users give some kind of input to the computer system for processing, and that input first of all goes and sits into the memory. Then the CPU or the processor fetches that data or instructions from the memory to the CPU and does the processing. And after the processing, whatever output data has been produced, that is also sent to the memory before it is transmitted to the output devices. So you see, the memory is the place where all the data and instructions are kept while the computer is working with them, right? And as you can see in this compute stack, here we have the hardware components and this is the memory. So all of the user applications require the memory, right? For storing the instructions which will be executed as part of the user application. And not just the instructions, they also need the memory to store the data that they will be processing. So this is how the memory is shared and needed by all the user applications in the system. So now that we have understood why do we need the memory, let us quickly recall what is the hardware interface that the memory exposes to the operating system. So now let us see how the memory looks like from the perspective of the operating system. So as you can see, this is the operating system, and the interface of the memory that is exposed to the operating system is that memory is an array of bytes, or you can also say it's a sequence of storage locations. So here in this figure, we have a very simple memory that is of 8 bytes or 8 locations, right? And with each storage location, we have a unique address associated with it, right? So since this memory has 8 location, you can see the addresses are going from 0 to 7. These addresses are continuous in nature. And as you can see, there is data stored in the memory. Now let us see how the interaction with the memory takes place. So any interaction with the memory occurs in the form of read or write operation. So basically in read operation, you want to get the data at any particular address, and in the write operation, you want to put some data at any particular location. So as you can see, this is the example. We are saying read from location 2. So here the address 2, whatever data is present at this address, we want to get that data. So in this case, 100 will be returned. And if you see the example for write operation, here we are saying write 50 to location 6. So this is the location 6 in the memory, and in this place we want to write the data 50, and that will be stored in this location. So this is how the interaction with the memory takes place in the form of read and write operation. And these read and write operation are also known as loads and stores in the context of the computer system. So now we have an idea how the memory looks like from the perspective of the operating system and what is the nature of interaction. Now let us talk about how the operating system manages the memory. So now let us talk about how the operating system manages the memory. So if we talk about the operating system, for any hardware resource, it performs two fundamental duties. That is, it first of all makes it easy to use by providing abstractions over that particular resource that are easy and much more powerful than the actual resource. And the second duty that the operating system performs is to ensure that the hardware is used efficiently, and that it accomplishes by doing a careful resource management. So first of all, let us talk about the first responsibility, that is making any hardware easy to use. Now let us understand what is the abstraction that the operating system provides in the context of memory to make it easy to use. So let us now see how the operating system manages the memory and makes it easy to use. So for that, I have a demo for you. In that demo, we are going to see that how the operating system creates the illusion of a private memory for all the processes in the system. So let us understand this point with a demo. So for this demo, I have a piece of code written in C, and later we will run this to understand or illustrate how does the operating system create the illusion of a private memory for all the processes in the computer system. So let us understand this code, what it is doing. So the very first statement here, we are allocating an integer value in the memory, and this pointer p, this is an integer pointer that is pointing to that memory location that we just allocated. Then we are setting the seed for random number generation, so that every time we run this code, a different random number is generated. Then we are storing a random number in that integer variable that we just allocated, and that random number will be from 0 to 999. After storing the value, what we are doing, we are running a loop for 20 times, and in this loop we are doing three things. First of all, we are printing a statement with three values. The first value is the process ID of the process from which this code is running. Then we are printing the address of that integer location, the memory address of that integer location, and then we are printing the value that is present at that integer location. And after printing these three values, what we are doing, we are updating the integer value, right? We initialized it with a random number, and then we are updating it, incrementing that number by 1. And finally, this in this loop we sleep for 2 seconds. So now you understand what this code is doing. First of all, it is allocating an integer variable in the memory, it is initializing it with a random number, and it is updating or incrementing it 20 times, and every time we update it, we also print the value. So now let us run this code and see how does it behave. So as you can see, I have already compiled this file memory.c, and the executable file is named memory. So I have opened two different terminals because I want to run two different copies of the same code at the same time. So let us run this and see what is the output. So as you can see, two different processes have been created. The process ID of the first one is 17,422, and in the second terminal you can see the process ID of the second process is 434. And the interesting thing is that the integer variable that we allocated, both of these processes have allocated the integer value at the same memory address, that is 4052A0, right? So now what is happening is that both of these processes are updating the same memory location at the same time. So as you can see, the first process has started with generating the random number 134, and it has incremented this memory location 20 times, and simultaneously the second process started with a different random number, that is 89. Here it was 134, here it is 89. And interestingly, the second process has also updated the same memory location, that is 4052A0 20 times, simultaneously running with the first process. So how does this happen? Clearly there is a mechanism that the operating system has created so that each of these processes has a separate memory of their own, because if they have the same memory, then how can they update the same memory location with different values at the same time? So now let us see how the operating system creates this illusion or mechanism where each of the process in the computer has a private memory of their own. So in the previous demo, we saw how the processes were updating the same memory location as if the memory was private to them, right? So now let us understand how does the operating system creates this illusion of a private memory for all the processes in the computer system. So let us start the discussion with this diagram. So this diagram is basically saying that this is the memory of the computer system, and it is called physical memory. And this is the actual memory, the actual hardware. And on top of this memory, the operating system will create the illusion. So the first idea, the first concept here is that of an address space. So what is an address space? An address space is a collection of memory addresses, right? So in this case, this is a memory with 16 locations, and with each location there is a unique address associated with it. So this collection, or you can say this set of addresses, that is from 0 to 15, makes up the physical address space. The name is physical address space because it is associated with the physical memory. So this was the first concept, that is of an address space that is associated with any kind of memory. So now let us see how the operating system deals with this address space. Basically, let's take an example. Here we have a hypothetical computer system where we have three processes A, B, and C, and this is the operating system. So what the operating system does is that it forbids these processes from directly accessing the physical address space, and it is only the operating system that can access this physical address space. So what is this figure trying to say is that these processes will not be able to access these addresses that are part of the address space of the actual memory in the system. Only the operating system will be accessing them, right? And as you can see, this memory also contains the data of these processes. This is the data for process A, this is for process B, and this is for process C. So now the question arises that if the processes are not able to access these physical addresses, then how can they access their own data, right? Let us now see that. So basically what the operating system does is that it creates a separate address space for each of these processes. So now if you see, there are three processes, and for every process the operating system has created its a unique address space associated with this process. So this is the address space for process A, this is for process B, and this is for process C. And these are the addresses, these are the only addresses that the processes will be able to access. So process A can only access these four addresses. It won't be able to access the physical address space. Similarly, process B will be able to access these four addresses, and same is the case for process C. And these address spaces are called virtual address space. The one that is associated with the actual memory, the physical memory, is called the physical address space, and the address spaces that are associated with the individual processes are called the virtual address space. So now let us see what is the relation between the virtual address space and the physical address space, and how the process can access its data via the virtual address space that has been allocated to it by the operating system. So basically what happens is that all the addresses in the virtual address space are mapped to some physical address. So in this case, the addresses in the address space of process A are mapped to the physical addresses that are associated with the data of process A. Same is for process B. These addresses are mapped to the physical addresses that where the data for process B is stored, and same is the case for process C. So now as you can see, this is how the processes will be accessing their data. Instead of referencing the physical addresses 1, 2, 3, and 4, the process A can get its data by accessing the physical virtual addresses 0, 1, 2, 3, and these are mapped to 1, 2, 3, 4. So in this way it can get its data. Similarly, process B will be accessing these addresses 0, 1, 2, 3, which are mapped to 7, 8, 9, 10, and that is how it will be getting its data. The same is the case for process C. So now that we understand what is the virtual address space and the physical address space, and how these two are linked with each other, let us now see how the operating system creates the illusion of a private memory for each of these processes. So if you carefully look at process A, then the only addresses that process A can access is 0, 1, 2, and 3 in its virtual address space. And these addresses will lead the process A to this region of the memory, that is from 1 to 4, right? So if you carefully see, the process A cannot access the physical address 0 or any of these physical address beyond the physical address 4. It can only access its own data via this virtual address space. Similarly, process B can only access these four addresses in its virtual address space, and these addresses will be leading the process B to only this region of the memory. The other parts of the memory are not accessible to the process B because they are forbidden to access the addresses in the physical address space. They can only access their own virtual address space. So if you see carefully what the virtual address space is doing, it is providing a limited view of the actual memory to the processes, right? So the entire view, the actual picture of the memory is forbidden from the processes, and the final view of the memory, or how the processes perceive this memory, is determined by the virtual address spaces. And mind you, these virtual address spaces have been provided by the operating system. So the operating system defines how the memory will look like to each of these processes. So this figure illustrates how the memory appears to the different processes, right? So if you see, process A feels that the memory is 4 bytes long and it contains only its own data, because the physical addresses that is reachable by this virtual address space lead process A only to this region of the memory. So it thinks that the memory is only this much and contains only its own data. The same is true for process B and process C. They feel that in case of process B, it feels that the memory is 4 bytes long and it contains the data, its own data, right? And if you see, all of this has been defined by the operating system. So the virtual address space and the mapping between the virtual address space and the physical address space has been defined by the operating system. And by carefully allocating this virtual address space and mapping them in such a way, the operating system is able to create this illusion for every process that this is how the memory looks like. Every process feels that the memory is private to it. So this is how the illusion of a private memory works. So this illusion of a private memory that the operating system creates for each of these processes is called the virtual memory. So these three that you see, these are virtual memories and this is the physical memory. So why is this memory called virtual memory? Because in reality, there is no actual memory or data present here. All the data is present only in the physical memory. This is where the hardware is. This is just an illusion. So this illusion has been created by the operating system by providing each of these processes with a virtual address space, then forbidding these processes to actually access the physical address space, and mapping the addresses in the virtual address space to the physical address space properly. So this is what the operating system does. And now for every process, the actual picture of the memory is hidden. They can only view the memory from this virtual address space. So this is just a view that is a subset of the actual memory system that is provided to each process. So virtual memory is just an extension of the virtual address space, right? Whatever memory that the process can see via this virtual address space is the virtual memory. So in reality, there is no data or memory here. It's just a view of the actual memory, and all the data in the system is present only in the physical memory. And if you see, in reality, the physical memory is shared between all these processes. There is nothing private about the physical memory. As you can see, all the processes have shared this physical memory. The data in the physical memory belongs to all the processes. It is not private to any particular process. This illusion that the operating system creates of a private memory, as I said, it's just an illusion, right? So in order to better explain you the concept of virtual memory, let me show you how the memory looks like, first from the perspective of the operating system and then from the perspective of these individual processes. So as you can see from this figure, this is the physical memory, the actual memory, and only the operating system has complete access to this physical memory. This physical address space is only accessible by the operating system. So the point is that only the operating system knows the complete picture, that the memory is shared by all the processes in the system and where is the data for which process, right? The entire picture of the memory is available to the operating system, and this is the true picture. Now for the individual processes, this physical address space is forbidden, so they don't have a true picture of the memory. It is for the individual process, the way they see the memory is defined by the operating system. Whatever the operating system will show them, whatever the operating system will create illusion for them, that is what will be visible to these processes. So as you can see, from process A's perspective, it only has access to these virtual addresses, and these virtual addresses lead process A to only this part of the memory. So from the perspective of process A, this is how the memory looks like. So it is very obvious that the process A thinks that memory is private to it because it can only access its own data. But in reality, this illusion has been created by the operating system. Similarly, for process B, it can access only its own data, basically via its virtual address space, and the same is true for process C. So you see how each of these process feels that they have a private memory, but in reality, the physical memory is shared by all the processes, and it's the operating system which has created this illusion for this individual processes. So this is how the concept of virtual memory works. So now let us talk about some of the benefits of virtual memory. As you can see, I have listed a few here. So the first and most important benefit of virtual memory is memory protection. So as you can see, even though the physical memory is shared by all the processes, that is, there is data from all the processes in the physical memory. Even then, via this mechanism of virtual memory, each process can only access its own data. Process A is not able to access process B or process C's data, right? If the processes had access to the physical address space directly, then they would be able to access other processes data, and this is not good because this violates memory protection. So this is one of the most important benefits of virtual memory. So the next benefit of virtual memory is that it provides a continuous view of the memory to the process and the programmer. So let us understand this point with an example. So till now we have assumed that the data of the process in the physical memory will be arranged continuously like this. But this is not necessary. It can be all scattered also. So for example, it can be arranged in a haphazard fashion like this. So if you see, even then, the view of the continuous memory will still be maintained. Although the physical memory, the data in the physical memory of each process is non-continuous now, but even then, since the virtual address space is continuous, we can create a mapping between the virtual address and the physical address space in such a way that the view of the memory that is exposed to the processes is still continuous. So even though the memory, the data in the physical memory for each of these processes is scattered and is arranged in a non-continuous fashion, the way the mappings have been done, and since the virtual addresses in this virtual address space are continuous, the continuous view of the memory is still maintained for all the processes. Another benefit is that we just saw that it does not matter whether the data in the physical memory is arranged in a continuous fashion or scattered manner. In both the cases, the view of the memory was same for the processes. It was a continuous view. So this is consistency. So now your view of the memory remains consistent irrespective of the manner in which the data in the physical memory is actually arranged. So this, as a programmer, is very essential, having a continuous and consistent view of the memory. That is what the virtual memory provides. It's a benefit of virtual memory. Another very important thing that the operating system does in the context of memory is that it not only creates the illusion of a private memory for each process, but it also provides the illusion that the memory is very large to each of the process. So basically it accomplishes this by increasing the size of the virtual address space. So let us understand this with an example. This is a computer system and this is the physical memory. And what the operating system has done, it has given a very large virtual address space to each of these processes. So if you carefully see, then the size of the, if you combine the size of these three virtual address spaces, then it is more than the amount of physical memory that is available in the system. Basically, the number of address mappings that will be originating from the virtual addresses is not sufficient to map to the physical address space, right? So basically what the operating system has done, it is advertising to the processes that there is more memory available in the system than there is actually available in the physical memory. And how the operating system solves this problem is that it uses the persistent storage or the disk. So some of the addresses will now be mapped to the physical memory. As you can see, for process A, some of the addresses are mapped to the physical memory and the rest of the addresses will be mapped to the disk. So now the operating system is using both the physical memory as well as the disk to store the data or back the virtual address space. So the way this works is that if the data is present in the physical memory, then it will be provided to the process. And let's say the process accesses some virtual address space, virtual address for which the data is not in the physical memory. In that case, the data will have to be fetched from the disk to the physical memory and then it will be given to the process. So this is how the operating system uses both the physical memory and the disk to create an illusion for the process that the memory is very large. It has increased the size of the virtual address space and now it is using both the physical memory as well as the disk to back that virtual address space. So thus the operating system creates the illusion of a private as well as very large memory for each of the processes in the computer. So we have seen that the operating system provides the illusion of a private and huge memory to all the processes in the computer. And this illusion has been created using the abstraction of an address space. Basically, the operating system has decoupled the virtual and the physical address space, and providing this virtual address space to each of these processes, it is able to provide the illusion of a private and huge memory to each of these processes. And this idea extends to the programmer also, the user or the programmer. So when you are writing your program as a programmer, you are given the same view that for your program the memory will be private and it will be huge. So now it becomes very easy to use the memory. Whenever you are doing some memory allocation, you don't have to worry whether that address will be used by some other program or not. You are given the illusion of a private memory. And in the similar manner, since the memory is huge, the illusion has been created by the operating system. You don't have to worry whether there is enough memory or not while writing your programs. So you see how the operating system, by providing this abstraction of a virtual address space, has made using the memory very easy. So this is how the operating system fulfills its first fundamental duty, that is making the memory easy to use. So now let us focus on the second fundamental responsibility of the operating system, that is to ensure that the hardware is used efficiently. Let us see how the operating system manages the memory and ensures that it is used in an efficient manner in the computer system. So this is the compute stack, and as you can see, there are several user applications in the computer system. Each of these user applications will be processing some data by executing some instructions, and these data and instructions have to be stored somewhere while the CPU is working with them, and that somewhere is the memory. So basically the memory is the place where the data and instructions of the processes or computer applications are stored while they are being executed. So as you can see, the memory is needed by all the computer applications. It's a shared and a limited resource. It has to be carefully managed so that the memory requirements of all of these user applications can be properly served. So this is how the situation of virtual memory looks like in the computer system. And there are many factors that the operating system has to keep in mind when managing the resource, that is the memory. So first of all, the operating system has to decide whether the memory has to be allocated in a continuous manner or a non-continuous manner like this, right? So as you can see, these are virtual addresses and they have to be mapped to physical address. When you map a particular portion of the virtual address space to a physical address space, that is when we say that the memory has been allocated, because the data will only be present in the physical memory. These are just addresses. So we need a way to map these virtual addresses to the physical addresses. So should that mapping be in a continuous manner or a non-continuous manner? Both have its pros and cons. The operating system has to take a careful decision, right? Another very important issue when it comes to managing the memory is the free space management. So these regions that you see, the gray regions, are the free regions in memory, and the operating system has to properly manage this free space, because it is this free space from where new memory has to be allocated. If it is not managed properly, then it can become fragmented. So as you can see, there is some amount of memory in this physical memory, but it is all scattered. So it could be the case that the total amount of free space is more than the memory that is being requested, but it is scattered in different regions. So in that case, the operating system will not be able to fulfill that request. So a proper free space management is crucial while managing the memory. Another very important issue while managing the memory is deciding which data will be placed on the physical memory and which will be placed on the disk. So basically the problem with the data that is lying on the disk is that if the process wants to access this data, then it has to do a disk access, and disk access is very slow compared to the physical memory. So it is good to have the data on the physical memory, but the problem here is that the operating system is providing the illusion of a very large memory, and all of these data cannot be placed in the physical memory. Some of them will have to go to the disk. So the operating system must ensure that the data that is frequently accessed or is more likely to be accessed should be on the physical memory rather on the disk, to avoid the penalty of doing a disk access. So this placement of data is also very important when it comes to managing the memory. Another very important issue in memory management is the situation when the data that has been requested by the process is not in the physical memory, it's on the disk. This situation is called as page fault, and it's an exception that has to be handled by the operating system. Why it is called page fault, we'll study these in later videos when we talk about the memory. But the problem where the data that has been requested is not found in the memory is known as page fault. And now it is the responsibility of the operating system to bring that data, requested data, into the physical memory. It might be the case that there is not enough physical memory in the system, and some of the data has to be moved out to make space for the newly incoming data. So now the operating system has to make a careful decision as to which data has to be moved out, because the data that is being replaced, if that is more like frequently accessed data, or it is more likely to be accessed in the future, then again for that we will have more page faults, and that is something that is not desired, because page faults are expensive and require disk access. So operating system has to take careful decisions, has to have good policies for replacing the data that is present in the memory. The final point that I would like to talk about, that is there in the context of memory management, is that this illusion of a virtual memory has been created by the operating system. And now for every memory access, the virtual address needs to be translated to the physical address. And this translation can take some time. It's the responsibility of the operating system to ensure that these virtual to physical address translations do not become an overhead for the system, because if we are spending too much time on translations, then this slows down the execution of the programs. So operating system employs different techniques to make sure that these translations take less time. For example, it caches these translation into a hardware structure that is called the TLB, which we'll study about in the upcoming videos when we talk about memory. So the point is that this illusion, this setup has been created by the operating system. So it has to make sure that this virtual memory system does not become a overhead. So we just saw several issues that are there in memory management, and the operating system has to keep in mind all of these issues for ensuring that the memory is used efficiently. There is the issue of memory allocation, free space management, placing the data on the memory or the disk, managing page faults, ensuring that translations between virtual and physical addresses are fast. So these are all the issues that comes when the operating system has to manage the memory, right? It has to ensure all of these are done properly so that the memory is used in an efficient manner. So guys, this was it for this video. In this video, we understood how the operating system manages the memory. It makes it easy to use by providing the abstraction of an address space. It creates the illusion of a private and huge memory for all the processes in the system. And there are several issues when it comes to memory management that the operating system takes care of to ensure that the memory is used in an efficient manner. So this was it for this video. Thank you very much for watching, and I'll see you in the next video. Thank you.